I work in two universities in TinyML, HAI, so I'm very passionate about. So I'm very passionate about the subject, and I'm very active in a way to bring TinyML, HAI to the local communities, to end users, especially in UK. The reason why I wanted to present this talk, it was last minute confirmation of my presentation. But the reason why I wanted to do this talk, because I feel this is a very important topic. It could be potentially the future of edge AI or even AI, decentralized AI, moving away from the cloud and servers or centralized infrastructure. Over the years, I've been working in pervasive computing area, and the motivation behind this area is to bring intelligence and AI, smart sensors to everyday environment, from retail to agriculture to parks and home environment. It happens that we had a project funded by the government which aimed to utilize 5G network in a big park. It's actually a forest, Robin Hood Forest, Sherwood Forest in north of Nottingham. And, but what happened is that the whole project was about utilizing 5G and showing innovation with 5G. And we had a few telecom companies. But what happened is that many of these companies couldn't set up a proper 5G to cover the whole park, because the park was very, very big, and the forest as well. So then we had, my team were aiming to embed little devices that can communicate and motivate people to move and be physically active and interact. We use some gamification approaches and so on. So we had to find another way to communicate between these devices using, 5G wasn't viable. We wanted even to, find internet access to download our apps, our services and so on, but it wasn't possible. So that's why at that stage, I started to think more and more about edge AI, on how can we utilize decentralized approaches to be able to process things away from centralized infrastructure. But also, beside that, one device wouldn't be enough. If you have a large number of people coming to a park, you need, to utilize all these devices. You need these devices to communicate. Like, for example, if you want to allow people to play a game and you want a scoreboard, you need some kind of a system where you can exchange information between these devices. So you need this kind of collaborative system that can process and exchange. So you need wireless communication and all of these tools. And that's why we started to think more and more with my team about the decentralized AI approach. And there are many names for it. So you'll see during my presentation, I call it distributed, I call it federated, I call it decentralized, because it's still a very much a new area in its infancy, and we're still trying to establish it. And I realized that I need many, many more days to add all the components that contribute to the system. So you might find some slides slightly messy in here. So, okay. This is just like a little illustration showing you like the vision in the future. Obviously, you will not see edge AI written on sheets in the future, but but at the moment, if you go to a farm north of Nottingham, you will see our collars with edge AI placed on cows who are not behaving at all. They have been chewing on our devices all day long, and on the solar panels that we printed. But that's the vision, that edge AI should be everywhere, but without you seeing the devices. They should be embedded. I don't know if you know the concept of disappearing computing. So computing is there, but you don't see it. It empowers people. And I don't need really to tell you how many devices are in the world. And I asked the question yesterday about like how many of these devices are utilized around the world. We still don't have, at least in the UK, still don't have a working wearable system, for example, for healthcare. We don't have even a working wearable system for anything other than, just a personal device that can be used for, general lifestyle. So there are many devices. Hardware, of course, can evolve, but there are a lot of chips out there, but we're not utilizing them. And these are potential resources that can be utilized. Oops. How do I go back? Okay, so what happens if we bring all of these devices and try to utilize their capabilities? Let's say, for example, in this room, we have, let's say, 20 wearable devices, whatever. Each device has 1 megabyte. Together, let's say, we have about 20 megabytes of processing power. Exclude about 2 megabytes for the communication, then you have 18 megabytes, which is much, much better for running a model than 1 megabyte or half megabyte. So that's the idea. What if we bring all of these devices together as a computational resource for resource sharing, but not just the memory, not just the processing power, but also other things. This device, for example, might sense something, the other device might sense something else, so they can complement each other's. And that's why, again, collaborative learning has been there for a long time. Distributed learning has been there for a long time, like, for example, using desktop devices to run something. Or federated learning is there as well. But the idea here is that if we have these edge devices doing their own thing, but then contributing to the overall model or learning, then we have a bigger resource. It's still not as big as data center, but it's still powerful enough. And imagine if you have 1,000, or like, for example, in the case of football match where you have so many fans with a lot of wearables, then you really have a considerable resources that can help at least in managing the event or coordinating chants or songs and things like that. So what happens if we distribute these tasks across all devices or multiple devices, multiple sensors, and then compress these features and make them float between these devices? And then you have all of these resources operating as one, reducing memory per node, and then you have a model, not necessarily bigger model. So you have, I will explain later how you have a local model and a global model. So again, just to put more emphasis on collaborative learning, because you could do distributed learning, each device can do its own thing, and this device is identical to the other ones, or each device can do something different. So take the case, for example, in the case of search and rescue scenario. If you have like a number of people trying to find a missing person, right? So you could ask 20 people to go in the field and find a lost child or a person. They all could have a camera and audio exchanging information. They all could be looking for a specific object or face recognition. But what if each device can look at the scene from different angle? And they work like to build a jigsaw. So each one can find, like, for example, this part of the body might be occluded where the other part is visible to the other person. So collaborative learning could be complementary. They could complement each other's. And then one angle is the body is visible from one angle, and then it might not be visible from the other side. So that's the idea. How can we do that in a way that each device can do something that is complementary to the other devices? But then also we could do parallel processing, not just on devices. We could do parallel processing on the device itself. So for example, if you are using a dual-core processor with TPU, let's say, for example, or NPU or extra processing units, you could distribute the model on all of these devices, on all of these processors, right? So for example, on ARM processors, you could use the M4, the M7, or in the case of the Google Coral, you could use the TPU And we've done that in multiple projects. And this could save time. So you don't want some of these processors to be idle while you are processing. You want to utilize each resource as much as possible because you really need these extra few bytes or these extra processing powers. And there are many types for parallel processing. I mean, you could, for example, do data parallel processing where each processor, for example, processes the same data. Or you could do a modular kind of processing where like each processor is taking part of the model and processing, and then all the features and the output of the initial model are fused to give an overall model. This is meant to be for later. And then, of course, I mean, we can't talk about this without talking about generative AI, right? Because everybody wants to do generative AI. But again, you know, like generative AI is very much interesting, but also power hungry, and it needs, much more processing capabilities. But again, here we have a better chance at utilizing wearable and distributed devices to run generative AI. And I have many students at the moment working on this. I mean, this is still work in progress. But you could imagine that you distribute, like, for example, you have a local domain knowledge. So this device is collecting different types of information than this one. So you have different domains interacting with each others. You might have different prompts. So just imagine, like, for example, here, with all your devices collaborating and giving me feedback, or like writing a story together, right? So everybody will be using different prompts, but collectively, we will build a story together. And I think that's very interesting for collaborative interaction, and that could be generative. I think I have a better slide for this. So the output will be localized summaries, actionable insights, and natural commands. But of course, I mean, generative AI is one way around it, but you could do any other kind of models. You could do different modalities. You could use sensing, you could do vision, and all sorts of things. Doesn't need to be generative. And there are many, many ways to do decentralization. Like, for example, in some of the projects, we have a heterogeneous system where we have different edge devices that are either wearable, they are drones, they are robotics, or they could be the same. Like, for example, when I mentioned the case of wearable in here, everybody has, for example, has a wearable device. So it could be the same type of device or multiple types of devices. They could be identical. Each device can do something different or identical. I mean, and also doesn't need to be big. It could be one-to-one, for example, collaborative system. Like, for example, two people walking around the park, having a conversation, trying to explore a topic. But there's an important element to this that normally the edge AI community doesn't think too much about it, which is communications. Because if you want to do this, you really need to think about communications, wireless communication in particular. So we're saying that we're not going to rely on the infrastructure, we're not going to connect to the cloud. So how do we communicate between these devices? So we need some form of communication, wireless in particular, short range or mid-range, but it has to be low power. And it has to be robust enough to enable that communication. And it also has to be available in a way that, or let's say, robust. Like I don't know if you know the concept of opportunistic networking, where nodes come to the network and disappear every now and then, or ad hoc networks, or delay-tolerant networks. These are old concepts in communications, but they are very important for these type of scenarios. Then when you start thinking about communication, you need to think about where to process, where to handle the communication, because you could run the models on the device itself, but then where do you handle communications? Still, you need the processor, the same processor, for example. So some of the things that we're trying to do, like to run a model on one processor and handle the communication on another processor, again, you are using some kind of parallel processing, but for different tasks. And beside the physical wireless communication, we need to think about the communication protocols. What kind of protocol that we should use to enable this type of interaction? On top of that, we think about continual learning, adaptive learning. And this is an important part of distributed systems. It's not like, for example, for other cases of wearable, you could use about personalization. You could choose to do continual learning. But in the case of distributed learning, the decentralized AI, we have to do it. And the reason for that is that we have to manage or overcome catastrophic forgetting. It's a concept where, for example, the model has learned something, and then you update the model with new data, and it might forget the previous learning. So we need to make sure that the model can be updated, but without forgetting the previous learning. And in our case here, if you have a lot of nodes, maybe I could show how this looks like. Just to explain the concept. It's very slow. Yeah, so you will have a local model to do the local data processing, but then you will have a global model. The global model is really floating across all the devices. And here, in the global model, where we do the continual learning, where we update the model, whether it's like updating or retraining multiple layers or the fine-tuning the final layer. And that's why continual learning is very important in this case. I'll go back to where I was very quickly. So because of the time limitation, I'm not going to be able to explain everything, but I will give you some examples of some of the things that we've been doing in my lab. If I can go back. Yeah, okay. So in terms of parallel processing, we've been using regular microcontrollers to test if we can, like, for example, do multitasking. And we have a paper, and you could read about our work in terms of parallel feature fusion, accepted recently for publication. The idea here is that you have one processor running image model, or CNN, and another running audio, CNN. And then you fuse everything and process the fusion on the M7, for example. So this is quite interesting because you could really save some time and reduce latency. But one of the key issues that we have faced, and that's why it's very important for us to work with hardware designers, is that we've noticed that there's no shared memory between the processors. So we had to find a way around it, like we had to hack it using procedure call, backcall, to be able to communicate the parameters between the different processors. But this is something very important. If we want to do parallel processing, we need this type of shared memory. We need the hardware design to take into account that people will be able to process multiple things at the same time, and maybe even having more processors, maybe 4 processors or more on the regular microcontrollers. And in this particular paper, we saved around 48 milliseconds by just doing this. So I will rush a little bit here. We applied similar thing for agriculture. We have multi-task on microcontrollers in the farm. Our devices in the field. We have LoRaWAN. We use ST has very good microcontroller with LoRaWAN interface. So sometimes our choice of microcontroller is not the memory or processor, it's the wireless interface or the other sensors that are available on the device. And another big problem, we talked about this, the datasets issue, where to find the datasets for the students to work on. This is completely a different problem, and we struggle with this all the time. And especially with distributed systems, like where do you get the data? How do you test this system? And where do you test it? Also, we did some experiments to see the running time on different processors. And then going to the concept of distributed system very briefly, this is the typical pipeline for edge AI. And And then I explained this briefly before. Again, we have a paper on the archive in this area to explain the concept, but more or less you have a model that tries to converge on multiple devices, and in this case, we assume we have hundreds of devices, many clusters, interclusters, and we average so we use a federated average to inform the different clusters. And the initial results showed very, very promising progress, but obviously it depends on the data set. I'm just rushing here. And we applied this in many, many similar scenarios, like what I mentioned before in the park. This is the park I mentioned earlier. We've been working with the Met Police because this is very important to be able, like for example, to find someone in High Street, by the policing services, or for example, for traffics or vehicular networks. Again, we have another strand of work. And let's see the last. Sorry, this is. Yes, just to finish this to say this is quite interesting, but it requires a lot of work. That's why we try to tackle many issues, whether it's the continual learning, whether it's the data sets, whether it's the where do you run this model, and how do you exchange the information? How do you deal with the gossip protocol, or do you use different protocol for the communication? But our biggest challenge, and I mentioned this to many of you, is the test bit. How do you test this? How do you evaluate it? How do you run the model? Because you need hundreds of devices to be able to do this. So sometimes we do simulation, but sometimes we use a small number of devices to run this. So this is quite difficult. So it requires more attention from the community. Very briefly, before I finish, we have some upcoming events. The retail event in July. We have wearable, AI on wearable, digital health in UK. I'm sharing this event. And then we have Edge AI Japan, Tokyo in October. If you're interested, please let me know. And finally, we have a new funded network called TinyML UK, where we will have a network manager to complement what Edge AI Foundation is doing to bring the Edge AI community in UK to collaborate with the wider community. But yeah, that's all.